All right, so we're going to start talking about inequalities again, but now we're going to talk about compound inequalities. And so we want to be able to write compound inequalities to model real-world situations and solve and graph compound inequalities. Before we can do that, we've got to know what a compound inequality is. And so a compound inequality consists of two distinct inequalities joined by the word and or the word or. Okay? A nice replacement for the word and is both, and a nice replacement word for or is either. Okay? Both and either or. And so what does that mean? Well, the difference between the two, the difference between an and an or, compound inequality, is basically in the words and or, what they mean. Right? If I go to the store and I want to buy pens and pencils, then I'm not going to leave until I have both. Right? If I go to the store and I need to buy pens or pencils, then I'm going to come to the first one I find and leave. I don't really care which one I get. I'll take either one. And so in a compound inequality, we're talking about solutions, always trying to find solutions. In an and compound inequality, the solutions I need to list, the solutions I'm looking for, are ones that will satisfy both inequalities. Because there are going to be two inequalities, and we want to make sure we're looking at the solutions for both of them, not just one of them. In an or, we'll take solutions from either one. We don't really care. So we need to consider and look at and graph both inequalities for both of the solutions for both of the inequalities, because we don't care which one we use. Okay? That is why, and I'll show you some more in a second, but in an and compound inequality, the graph contains the overlap of the graphs of the two inequalities, because the overlap will show us the solutions that work for both inequalities. In an or, it's just graphing each of the two inequalities and knowing that we can use either set of solutions. Okay? So, inequalities with the word and would be something like this. X is greater than 3 and x is less than 7. Okay? Well, if I were to graph the solutions for both of those individually, right? Here's 0, here's 3, here's 7. X is greater than 3. Open circle on 3, and I would shade this way, right? Open circle on 3 and shade this way. For x is less than 7, I'd put an open circle here and shade this way. Well, where are the solutions that work for both? Well, they're all in here, right? So if I want to graph this compound inequality, then I'm looking for solutions that work for both. The solutions need to be greater than 3 and less than 7 both. And that's where this graph down here below comes from. We can't include 3 and 7 because 3 and 7 are not solutions to both inequalities. So we have an open circle on 3 and 7, and we're shading in between them. And since we're shading in between them, it opens ourselves up to some more notation here. So when we have an and compound inequality, very often it's okay to write it like this, where x is in the middle of two less than inequality signs with our two numbers on the outside. And that will be read, 3 is less than x, which is less than 7. It means I need solutions that are greater than 3 and less than 7. And that's right there. Okay? Now, one more thing to say about ands. Given a compound inequality such as that, you would read that as x is between 5 and 10 inclusive. And the word inclusive here means that we want to include 5 and 10 in our solutions. Right? And we do that because we're writing these as less than or equal to. Okay? All right, or compound inequality means I'll take solutions from the first inequality or the second, and I don't care which one. So quite simply, if I show the solutions for the first inequality and the solutions for the second inequality, then I know that any of those numbers will work for my or. So you simply graph them individually, and that's what you see down here. Okay. All right, let's get into writing these and solving these. So if I wanted to write this compound inequality, I need all real numbers that are greater than negative 3. So I need my solutions to be greater than negative 3 and less than 6. So I'm looking at an and compound inequality. I want them to be greater than negative 3 and less than 6. Then that means my solution is going to be between negative 3 and 6. So when I graph them, I want all the numbers that are greater than negative 3 and less than 6. And those numbers are all right here in between them. Okay? Open circles on negative 3 and 6 because they're not part of the solutions. They're not part of the solutions because their inequalities are not equal to. Negative 3 is not greater than negative 3, and so on and so forth. Okay? I'm trying to write this one. All real numbers that are less than 1 or greater than or equal to 3. What's an or? Ors are a little bit easier. We can simply write each one individually. X is less than 1 or X is greater than or equal to 3. Would look something like this. Open circle on 1, and we want to be less than 1, so we're going to go this way. Closed circle on 3, and we want to be greater than 3, so we're going this way. And that's it. Okay? All right. Now, solving. Okay? If I want to solve an and compound inequality, and very often we're going to write them like this, where they're that merged sort of inequalities, then what I would do basically is look at this and say, all right, if I covered up this inequality, what would I do to solve that one that's left? Well, you would subtract 3 from both sides, right? And if I then covered up this inequality, what would you do to solve that one? Well, you would subtract 3 again, right? So no reason why we can't do that to both of the wings. Right? So basically, when you're solving a compound inequality, an and inequality like this, whatever you do in the middle to isolate x, you have to do on the wings as well. So, all of our solutions are greater than negative 5 and less than or equal to 1. Greater than negative 5 means an open circle. Less than or equal to 1 means a closed circle, and we're going to shade in between. Those are our solutions. Okay? Next one. It's the same thing, right? What would you do first if I covered up this part of the inequality? Well, you would add 3 to both sides, right? What would you do first if I covered up this inequality? Well, you would add 3 to both sides. So that's what we're going to do. We're going to add 3 here in the middle, and then add 3 to these guys as well. So we get 2x in the middle here, 8 goes here, 13 goes here, and then the same thing. To isolate x, we've got to divide by 2, so we're going to divide everything by 2. So we're left with x. So now our solutions are greater than 4 and less than or equal to 6.5. So where are those numbers? Well, they're greater than 4, less than or equal to 6.5, and they're right here in the middle. And we're done. Okay? Now you try one. Stop the video. Isolate x. Remember that whatever we do in the middle, we got to do to the wings, and then go graph. Did you get this? Add 16 to the wings, and then divide the wings by 3, and you'll have x isolated. So 4 is less than or equal to x, which is less than 7. And when you graph that, we need a closed circle on 4 because that inequality is equal to, and that makes 4 part of the solutions. And then open circle on 7 because 7 is not going to be part of the solutions. Okay? Good. What about something like this? Right? Where we've got fractions, right? And we've been talking about these fractions a little bit, and I'm going to continue doing this the way I've been talking to you about it. I want to make all these fractions have a least common denominator, and most of you guys can do this without a problem. Well, the least common denominator is going to be 4. So I got to multiply this guy, numerator and denominator, by 2 to make the denominator 4. The middle guy, I don't have to do anything for. The right-hand side guy, I've got to multiply the numerator and the denominator by 4. And so we're here. And now that we have common denominators, we can just erase them. And that comes from if we multiply each term by 4, the 4s would just divide out. So there you go. 2 is less than or equal to 3x plus 1, which is less than 28. And now you're ready to solve like you did the last problems. Subtract 1 from both sides. Well, not both sides, all sides. Right? And then divide everything through by 3. So we get 1/3 is less than or equal to x, which is less than 9. And now we're ready to graph. 0, 1, 9's out here. 1/3 is probably going to be about right here. Closed circle because it's equal to, and that inequality sign is equal to, and so that means that 1/3 is part of the solutions. Open circle on 9 because it's not going to be part of the solutions. And shade in the middle. Because we want numbers that are greater than 1/3 and less than 9. Okay? Think you got it? Try 7, doing the same thing. Okay, there you go. Get a common denominator of 5, which means I'm multiplying the numerators, the -3 and the 3 by 5 to get negative 15 over 5 on the left side and 15 over, that should be a 5 on the right-hand side. Then drop the denominators and go solve. Subtract 8, divide by 2, but remember when you divide by a negative, you've got to flip the inequality sign, so make sure that you do that. And so that tells us that the solutions are greater than 3.5 and less than 11 halves. And that's what I've got graphed there. Okay, so make sure you turn those inequality signs. Got another one here for you. Give that a shot, stop the video, start it back up and see how you do. Okay, this is what you should have ended up with, and I hope that you did. If not, come on in, sit with me, and we'll figure it out. Okay? Now, or compound inequalities, a bit easier. Again, I'll take solutions from here or from here, and I need to show the solutions from either one. So we're just going to solve each one and graph them. That's it. Subtract 5, subtract 5. T is greater than 6. Or add 10, add 10. Divide by -2. So T is less than or equal to -15. And so since I'll take either one, then I want my solutions to be greater than 6 or less than or equal to -15. Okay, and there we go. Go ahead and give this guy a shot. Solve each one, graph them, and those are going to be your solutions. All right, so the first one, we're going to add 8, add 8. Divide by -4. Make sure that you flip that inequality sign around. And then for the other one, we're going to subtract 7, subtract 7. Divide 3, divide 3. And so x is greater than 6. So I need x is less than -5 or x is greater than 6. It doesn't really matter where we pull our solutions from. So open circle on 6 because it's not equal to, therefore 6 is not a solution. And we're going to shade greater than. Open circle on -5 for the same reason. And we're going to shade to the left because we want our solutions to be less than -5. And there we go. Which means that anything in the middle here is not going to work. It's not going to work because those aren't solutions for either one of them. Okay? All right. Another one. Try this guy. Stop the video. See how you do. Did you get this? X is less than 1/2 or x is greater than 4. And there's your graph for both of them. Okay? If this is still a little confusing, make sure you come in and see me. Okay, quick story problem involving these inequalities. Algebra 1 teacher is given 3 tests. You want to earn a B in the class. So you must achieve a test average between 83 and 86 inclusive. Remember, inclusive means that we're including 83 and 86. You've scored a 79, an 88, and an 82 on the 3 tests so far. What possible scores can you earn on the 4th and final test to earn a B? All right, so we want our average to be between 83 and 86 inclusive, which means that we're going to be equal to. We'll take equal to 83 or 86, right? Well, how do you find the average of 4 numbers? Sure, you simply add the 4 numbers up. There's the 3. The 4th one we don't know, it's x. So that means it's time to define our variable. X is the score on the 4th test. And then once we add those 4 numbers up, we divide by 4. Okay, and now we've got to go solve. Well, we can combine those 3 test scores first and get 239. Wait. 249, sorry, 249. Plus x over 4 is less than or equal to 86. Then I'm going to make these all have common denominators by multiplying the numerator and denominator by 4 on the wings. So we get 332 over here, over 4, less than or equal to 249 plus x over 4, less than or equal to 344 over 4. And then I'm going to drop the denominators because I don't need them anymore. Then I'm going to subtract 249 from everybody. And so this is going to be 83 is less than or equal to x, which is less than or equal to 95, which means that in order to maintain this b, you need to get anything anywhere from an 83 to a 95 inclusive, which means that we'll take equal to. And there you go. Okay? All right. A couple last things here. In order to qualify for the child rate at Holiday World, a person's age must be greater than 2 and less than 12. How would you write that? It's an and. You've got to be greater than 2 and less than 12. That's pretty much it right there. And to graph, open circle, you can be any age in between 2 and 12. Just can't be 2 and can't be 12 because you still won't qualify. Be either too young or too old at that point. Okay? An example of an or, right? Water is non-liquid when the temperature is 32 degrees below 32 degrees Fahrenheit or below. Or is at least 212 degrees, right? At least means could be hotter. Obviously, those are the freezing and boiling points of water. So when is water non-liquid? Well, it's non-liquid when it is less than or equal to 32 degrees, or when it's greater than or equal to 212 degrees. Right? And there you go. So 32 here, 212 here, close circle on 32, and we'll take everybody less than, open circle on 212, and we'll take any temperature greater than, and the water will be non-liquid. And there you go, an example of an or compound inequality from a bit of a story problem. Okay? And that's all there is to compound inequalities. Homework's out in Canvas. Make sure you have that done next time.